Hey everybody, this is just a quick answer key for activity 7.1. So more than likely this is because you did the alternative version, or I know some years it's a self-paced lesson, other years we go through the lesson together as a class. So for the most part, this is going to be the answer key, and I'm assuming you've already gone through and answered all the questions and you watched the videos that are associated with the lessons. So our learning target is we're going to learn how sound energy is different from other types of energy. So let's just say for a second, humor me. Can you tell when a ball is bouncing even if you don't see the ball? For example, if I bounce a ball, even though you can't see it, could you hear it bouncing? Yeah. So we're going to be talking about sound today, and we're going to be going through the answer key. So you've already watched these videos. They're all embedded within the self-paced unit guide. Then you're supposed to answer some questions. So what happens to the skin of the drum when you strike it? And which way does it move? So you should have seen that it vibrated. And it vibrates from the inside out. So if you hit that drum right in the middle, it's going to be vibrating inside out. And it looks a lot like a pebble that you throw into a stream where the ripple marks or the waves go out in all directions. So the same thing happens when you strike the skin of a drum. Does it move fast? Yeah, I mean, it moves incredibly fast, and it depends on, how tight the drum is and whether it's designed to make a really, crisp noise or a really deep, deep noise. So what does the drum skin do to the air molecules around it as it vibrates? Well, it vibrates the air molecules, and that's how you hear it. So you strike the skin of the drum with the drumstick. It vibrates the drum, and that drum skin vibrates the air, and that's how we hear drums. When does the air around the drum have more kinetic energy? Before it was struck or after? Obviously after it was struck. Before it was struck, you don't hear anything. Where does this kinetic energy of the air come from? Well, the kinetic energy of the air came from the skin of the drum, which came from you striking it with the drumstick. If the air is getting energy from the drum, what should be happening to the energy of the drum? Well, it's going to dissipate. It's going to be getting lower and lower and lower. And think about it. If you strike a drum, yeah, it's going to make some noise. And some of them will make a noise for a little bit, but eventually it stops. So where did all that energy go? Well, a lot of it went into the air, and you heard it as sound energy. So if the drum skin energy decreases, what should happen to its vibrations? Well, they should also be decreasing. There should be less of them. How can we tell this is happening? Does the drum skin stop vibrating, or does it keep going? Well, it stops. Obviously, it stops vibrating. And which drum makes a sound that fades away faster? One that makes a loud sound or one that makes a more mellow sound? Why? Typically, it's the louder sound fades faster. And it's those deeper drums that you hear that they vibrate, and sometimes it feels like they're vibrating within you. And in my new classroom, I can actually hear the mellow sounds, the drums that have the deep bass type sound more than I can the other drums during band because the walls are so thin. All right, so sound. Sound is what we hear with our ears as a result of air moving in a coordinated manner called a wave. When something makes air molecules all move together in a coordinated manner so that they do not actually move far from their positions, the result is something we call a sound wave or sound vibrations. When this wave gets into the ears, it's detected and a signal is sent to the brain where it's interpreted as sound. So sound waves can even be felt on the skin. If they are loud enough, people who are deaf can actually feel the sound vibrations although they can't hear the sound waves. And that's something that's really cool. So when we think of sound, think about how much time and energy goes into learning how to speak. And when you say a certain word, you have to say it in just the right way so that you make just the right sound so that our ears pick up just the right sound so we can recognize that sound. So it's pretty neat that we're able to do that. So here are some more questions you got to answer in part 2. What other devices do you know that have sound energy? Answers are going to vary. Bouncing ball, ringing bell, boiling teapot, subwoofer, springs. Almost everything these days seems like it has a sound. Where does the sound energy of a bouncing racquetball come from? Well, the sound energy from the ball's energy. So if you drop it, excuse me, think if you drop it from a distance, that GE is turning into KE. And that KE eventually, when it strikes the ground, is being converted into EE, but some of it is also being converted into sound energy. And eventually, the ball stops bouncing because all the energy, all that gravitation, all that kinetic energy was converted into different types of energy, such as thermal energy and sound energy. Does this sound energy have something to do with why the ball stops bouncing? Of course it does. One of the reasons the ball stops bouncing is because it loses energy in the air as sound energy, so it has less energy to keep it bouncing. So then you're supposed to draw an energy transfer diagram that shows the bouncing ball transferring energy to its surrounding. How did you do? So we have a bouncing ball, we have KE, GE, EE, TE, sound energy, and it all dissipates as thermal and sound energy. Ideally, this is what the book had. Ideally, you might have had a title like here, the bouncing ball. Where did it convert it into? You might have had the ground and air, because obviously it would have given some energy to both. And then it would have basically been thermal and sound energy. And then you were supposed to answer the making sense question. Why, when popped, does a fully inflated balloon have a louder noise than a partially inflated balloon? Well, first of all, when we look at the balloons, if it's fully inflated, it's got a lot more EE. It's been stretched more. And if it's got more EE, that means it's going to make, well, it's got more energy to give and to transfer. So that's why it's going to make a louder noise. And then we've got we got a few scientific principles to add. Let me get there. Here they are. So add these scientific principles to your book. Sound is associated with the coordinated back and forth motion of particles. And when an object emits sound, it loses some of its energy to the surroundings. Now, when we went through this presentation, you probably saw lots of links to the videos, and we're actually going to do some demonstrations, and we're going to watch some of those videos together as a class. The only videos I had you watch were the ones that you needed to watch to finish this. The other ones are fun ones. We'll watch together as a class one of the next times we have class. So as always, if you have any questions, make sure you ask, and make sure you have corrected all the wrong answers in your book so you have them correctly in your book so you can use them on a test. Thanks. Bye.